Hi. All right, we're in asynchronous week 10. Guys, it's late October. Before you know it, this class will be over. I know it seems like a long time, but we're more than halfway done. Just so you know, I did get the email today that your midterm grades are due Monday at, I don't know, 5 p.m., 7 p.m., something, 5 p.m. So your midterm grade will be posted by then, which means I have to have your test graded by then. So I will have your test graded by Monday at 5 p.m. so that I can submit your midterms. So that's good for most of you anyway. I'm forgetting something, but I am not. Okay. So we're going to be starting chapter 8. In this class, every time we start a new chapter, it's very different from the previous chapter. So unlike with Calc 1, where you were just sort of continuing topics and building on them, we're completely shifting in another direction now. You'll see that what we're going to be doing now sort of relates to what we were doing back in 7.7 when we were talking about improper integrals and whether or not we had some convergence or divergence. The difference is that now we're going to be talking about sequences and series. Now, these sections aren't really particularly hard. They are really just adapted from ideas you've already learned about. Some of this you learned about in college algebra when you learned about, for instance, sequences and series, and you learned about geometric series and how to find the sums of series. College algebra, algebra 2. I know if it's been a while, obviously I'm going to show you what you need to know. There's really nothing from algebra that you have to know here. It's more of just like, don't worry, this is a lot of stuff you've already gotten familiar with before at some point. So I'm going to start with 8.1, which is about sequences. Now, I always feel like I need to note to students, most of this chapter is not about sequences. It's about series, which are very different. Now, when you go to take your chapter 8 exam, I'm going to have to remind you of like, okay, I'm asking you about a sequence, not a series, because you're going to get so used to working with series that you're going to forget everything there is to know about a sequence. So I'm going to give you this information now, and I'm going to remind you before your test to brush up on your sequences so that you're prepared. They're not that hard. There's nothing crazy in here with the sequences. It's more of just like, are you going to remember at the end of the chapter what a sequence is and how to work with a sequence? So this is chapter 8, section 1. I'm going to give you a definition. A sequence is a function whose domain is the set of positive integers If you don't remember what integers are, they're whole numbers that can also be negative, but in this case, we're only talking about positive integers. So we're really talking about whole numbers. However, whole numbers also include 0, and we're only strictly talking about positive integers here. So we're talking about the natural numbers, 1, 2, 3, 4, 5, 6, 7, so on and so forth, and whose range is a subset of the real numbers. Wonderful. I'm going to give you probably even some more definition here. Every time you see a sequence in this book, it's going to be displayed with parentheses around it. And not parentheses, I'm sorry, braces. So when you see a sequence, it will have braces around it like this. And your sequence, I mean, obviously this is going to depend on what the actual function is, but usually we just denote it with a sub n. Now, whatever the sequence is, it'll be inside the braces. I'm just writing it as a sub n just because that's usually how we note a general sequence. The values of the function f of n are called terms of the sequence. So I told you a sequence is a function. So the values of the function, and we usually denote anything with sequences using n and not x, because we're really just denoting that these are going to be positive integers, kind of sets apart the sequence from a regular function. So the values of the function are called the terms of the sequence. N is called the index. So I'll just kind of mark that. So really, if you're thinking about a sequence, A sub n, you would just write out the terms of a sequence by just starting at 1. So you're starting with positive integers. So you would write out A sub 1, A sub 2, A sub 3, A sub 4, dot, dot, dot. And this would just sort of tell you that, okay, these are the values in the sequence. So of course, it all depends on what function is inside of this sequence. But these are your terms, A sub 1, A sub 2, A sub 3, A sub 4. You're going to see a lot of these ellipses as we work our way through this chapter. It just sort of denotes like, okay, this behavior is going to be continuing on in this pattern. And obviously you don't have the rest of your life to just die writing this sequence out. So you're just sort of indicating that like, okay, this behavior continues throughout. So the little number here at the bottom, the subscript is the index. Now the sequence does not have to start at n equals 1. It can start at any other integer. So kind of just depends. Normally we would start evaluating a sequence at 1. So just some basic concepts here having to deal with sequences. I'm going to have you do something similar to what you're going to see on your homework. Let's see. Oh, goodness. I thought they changed up their notation here, but they did not. They sort of did. Interesting. Okay. So you're going to be asked to write out terms of sequences, and we're going to do that. And I don't think anyone here is going to have a hard time with that. I'm also going to have you do it on the test, and it should be like easy points. If you get it mixed up with a series, then you'll lose the points, and that will be really unfortunate. Example 1, write the first 4 terms of the sequence. Oops, I'm running out of space here. Okay, so like I said, this should be easy points right here. So let's say that we're looking at a sequence, and I'll give you this written as, let's see, I'm going to match your book notation. They're writing this as S sub n and not A sub n, which is fine. It does not matter. Just want to match what they do. So our sequence is going to be 1 over 2 to the nth. You know what I do, though, want to make sure that this looks like a little s and not a capital S. Kind of hard to do that with a subscript. So for a sequence, we would think about this as being a lowercase s, whereas with a summation that we're going to be doing with series, that's a big sum. So we denote that with a big S. So not the end of the world as long as you know how to find the terms. I just want to make sure to make that distinction when I write it out. All right, so when we're finding the first 4 terms of the sequence, we're going to start out with S sub 1, then we'll find S sub 2, S sub 3, and S sub 4. So all you're going to do is just, and by the way, I'm going to write this out as S sub 1, S sub 2. If I asked you to do this on a test and you just said equals blah, 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 ellipsis, that's fine. But I'm just going to separate mine out here. So if n equals 1, we would have 1 over 2 to the first, which is a half. So that would be the first term in your sequence. And then you would just do this again to find the second, third, and fourth terms in your sequence. So looking back at your nth partial sum that I gave you, and this would be 2 to the second power, which is 1/4. And, just by looking at this function, you should have a pretty good idea of what you're expecting to see here as far as the behavior of these terms. So 2 cubed is 8. So, each time you're seeing the numerator is just going to be 1. And the denominator is just another power of 2. So if you said on your test that the first 4 terms were, and then you said a half, a fourth, an eighth, a 16th, this answer would be completely fine. Okay, so that's just one basic example of how to find these. I do want you to see different types of sequences, however. One of them that you're going to see is the kind of sequence, and we're going to be dealing with these types of numbers actually a lot throughout the chapter, where you have this sort of oscillating piece to it. So something like -1 to the nth power, and then the rest of the sequence will look normal. But what you get when you include something like this is you end up just getting the sign to change between each term in your sequence. Notice that if n equals 1, this sign is going to be -1. But if n equals 2, when you square -1, you get +1. And now you're going to get a positive term for s sub 2. And then it's just sort of going to go back and forth between negative and positive. And like I said, this is going to be something that we're going to see throughout this chapter. All right, so let's see, s sub 1. When we let n equal 1, we'll just get -1 to the first. And you can just, evaluate it like this, whether you write the 1 or not. It does not matter. I'm writing it just because I'm the one evaluating it. And your first term is going to be -1/2. Still running out of space. Oh. You know what? That'll work. That's why. S sub 2. This time I'm going to take -1 and square it, but my numerator is going to change in more than one way because I now have a variable in the numerator instead of just 1 like I had in the last example. And we'll have 2 squared plus 1. So I'm just following along with this function, and everywhere I see n, I'm subbing it out with 2. So this will be a +2 in the numerator. 2 squared is 4 plus 1 is 5. For the third term, you'll have -1 to the third power times 3 divided by 3 squared plus 1. 3 squared is 9, plus 1 is 10. And then for the fourth term, same thing. -1 to the fourth power times 4, and then we'll have 4 squared plus 1. So -1 to an even power is going to be +1 times 4 is 4. 4 squared is 16 plus 1 is 17. And double check that your sign changed from one iteration to the next. So it was negative, positive, negative, positive. And then you're seeing with your denominator that each time you have a perfect square plus 1, perfect square plus 1, so on and so forth. And then 1, 2, 3, 4. So this would be -1/2, 2/5, -3/10, and 4/17. So this would be the first 4 terms of your sequence. And as long as you labeled them and listed them out, you don't have to rewrite it again. I just kind of wanted you to see it both ways. But I mean, if you're thinking you're not really going to have to do very much of this on your homework, there might be. Actually, I was going to have you do it next. But there won't be a ton of this, but I want you to start thinking at this point about how you would have worked your way back from here to here. Because what we're going to be doing next is I'm going to be asking you to find a formula for the nth term of the sequence. So like if you know the first several terms, how would you be able to write this formula? And in a lot of cases, it really just comes down to just recognizing the relationships between the numbers. Like, for instance, being able to recognize that, like, okay, really, there's not a lot in common between these values. What a lot of students tend to see between these is to get from one denominator to the next, they're thinking, okay, well, if I add 3, then I add 5, then I add 7, I'm adding an odd number. But let's say you had 16, and then you go up to, so 4 squared, 5 squared is 25. You'd be adding, to get to 26, 9. So, I mean, that technically works out, but it's more important to understand the broader relationship between these, which is that all of these values are just one more than a perfect square. And sometimes that can be kind of hard to see. But if you're ever trying to represent this oscillating term where you go from negative to positive and back and forth, you'll either use -1 to the n or -1 to the, you can do n plus 1 or n minus 1 if your first term was positive instead of negative. So that's always an option as well. And then because the numerator just goes 1, 2, 3, 4, well, that's where your n comes from. So just kind of be thinking about that. We're going to do that in the next example. You're going to see a couple of these in your homework. It's not like a huge emphasis of mine for you to see that, but I do think that there's value in it, so we'll do that. Example 2. Find a formula for the nth term of the sequence. So I'm going to give you some terms of a sequence, and then I want you to find a formula for it. Now, I'm trying to figure out how tricky I want to be with this. I don't want to be super tricky. Okay, I'm going to give this to you in a more simple form because you're not going to see anything that's tricky on your homework. So I don't want to do anything super crazy and then have you be like, okay, that wasn't helpful. But I'll also rewrite it at the end so that you could sort of see where this came from. So we're going to go with -1, and then, and I'm already regretting this. I'm always changing my mind all the time where I'm like, yep, this looks good. And then when I go to teach it, I'm like, I don't know how I feel about that. Okay. So I'm going to give you these terms. Now, notice that I did not give you these terms as simplified fractions because that would have made this a lot harder. If these were unsimplified, you would have had -1, 1, -2/3, 1/3, and then I don't even know what 16 divided by 120 is. 2/15. And this would have been a much harder, why are there 2 lines here? This would have been a much harder problem to do because it's much harder to see the relationship between these values. So that's something to keep in mind. If you did see something that was written like this, one option that you have is to try to unsimplify the fractions to see if you can find some sort of pattern within their denominators. I mean, especially when you see that your numerator is going down again before it goes up, that would indicate to me that you could make this much bigger by unsimplifying it pretty far. This one maybe a little bit less so, and then just trying to sort of make some sort of connection there between the values that you have. But anyway, this is the sequence that I want you to work with because I'm not going to give, I certainly wouldn't give you anything complicated like this on an exam. So, I just want to make sure we understand that these are the same. One of them's just more complicated. But what you're looking at here is a situation where, first of all, it's really important to notice that your terms are oscillating. Oh, you know what I did? I got off on this kick where I was going to change something and I didn't. And the one thing I was going to change, we're going to change it now just because in the last example you saw something where the negative sign started out on the first term being negative. I'm going to switch them. We'll put the negative signs on terms 2 and 4. That's what I want to do. I want this to look different than the example you just saw. All right, ready? So I'm going to start building my nth term of the sequence. I'm going to get a general formula for it. In order to do that, I need to start picking up some relationships between these values. If you want to first write the oscillating factor, that's fine. You know it's going to be -1 to the something. It's either going to be n or n plus 1. I mean, technically, you could also use n minus 1. We just usually use n plus 1. Either way, n plus 1, n minus 1, they mean the same thing in this type of instance. So if I were to write -1 to the n, and then if I were to let n equal 1, well, my first term would be negative in that case because -1 to the first stays negative. But we left this positive. So that's how you can check. You can say, wait, well, it can't be this one. So you can always default to this one. And then if it doesn't work, switch up your exponent to something like n plus 1. So now you can check it again and say, okay, well, my first term is supposed to be positive. If I let the first term be n equals 1, which it always will be. So our first term represents n equals 1. 1 plus 1 is 2. -1 squared is positive 1. So we do indeed have a positive sign. And you could always test it again for another term. So like if you let n be 4, so n equals 1, 2, 3, 4. If you let n be 4, 4 plus 1 is 5. -1 to the 5th power is going to stay negative. That does indeed work. You know, just check it and make sure that your formula is correct. Okay, so now you need to start picking up some sort of relationship between the numerators. Now, if you'd like, you can write 1 as 1 over 1. You might not feel like it's that helpful, but if you'd like. So you're seeing your numerators go, let's look at the absolute values, from 1 to 2 to 4 to 8 to 16. So we sort of looked at this idea in the previous example where or I guess it was 2 examples ago, where we talked about taking 2 to the power n. So if we took, 2 to the 0, we'd get 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16. So try to get out of this habit of thinking about these values as being like, okay, well, I'm going to multiply by 2, by 2, by 2. Technically, that's what you're doing, but think about it as being a power and not like a multiplication type of problem. All right, so we know we're looking at some sort of 2 to the n, but notice that for your first term, n equals 1, if we're using 2 to the n, then this numerator should be 2, and it's not. It's 1. So you need to consider the fact that 1 is just 2 to the 0. 2 is 2 to the first. 4 is 2 to the second. 8 is 2 cubed. So notice that in each case, your exponent is going to be 1 less than the value of n that you have. So if n is 5, the exponent's 4, so on and so forth. So you can write this as the n minus 1th power. And again, double check it if you're not sure. Plug in some values, make sure it works for you. But if I let n be 1, 1 minus 1 is 0. 2 to the 0 is 1. So you can match that up. I know it's tricky. It's one of those things where when I do it, it's like, oh yeah, totally got it. But then when you have to write your own, sometimes it can be tricky. But hopefully there's nothing on here that you'll find super crazy. There's, who knows? I mean, the ones in the book are not. I guess I was just wondering, like, what will Achieve have in there? They might not even cover them. This might be a waste. Okay. Now let's think about your denominators. Okay, I'm going to remind you of something right now that you haven't seen probably since you were in college algebra. called a factorial. If you don't remember it, I'm going to remind you of what it is. We're going to be using them a lot throughout this chapter. So factorial is when you multiply successive values together. So like 1 times 2 times 3 times 4 times 5. So if I could give you an example, like a general example, n factorial would be 1 times 2 times 3 times 4, all the way up to n. If I was just going to give you a more basic example, like 3 factorial, that's just 1 times 2 times 3. So you're just always starting with these natural numbers and working your way up to whatever value that is. So of course that would be 6. But so on and so forth. But I might as well, since we're looking at 6 actually being on here, if n equals 3, 3 factorial is 6. But you can do the same thing for 4 and 5. When you take 6 and multiply it by 4, you get 24. Well, look at your denominator. If n is 4, your denominator is 24. And this is where your factorial comes from. So it's one of these things where just looking at the numbers, you could get so frustrated because you would just be wondering, I can't find the connection between these. What am I supposed to do? It's really just about getting familiar with these concepts, seeing them used over and over again, and just sort of getting an understanding for how everything works together. We can do the same thing for 5, but 24 times 5 is 120. 4 times 5, yeah, 20 times. Okay. And that is, of course, the denominator for n equals 5. So if you're not sure, try a factorial and see. Now, factorials get very, very large very quickly. And yes, these are exclamation points if it's been a while since you've seen these. Factorials get really large really fast. So that's another thing that you could be thinking about. If your numbers get super large super quickly, you might have a situation where it's like n factorial minus 1 or something. It might not exactly be 120. It could be close. So just kind of note the relationship between these values. So we would say in the denominator that we have n factorial. Now this one was a little trickier than even just the ones I see in the book for your homework. I just mostly wanted to give you an example that included more stuff to it so that I didn't have to give you a bunch of little small examples. I just kind of wanted to put everything together. I thought that'd be more helpful in this instance. All right. Now, we are going to go further into our discussion of sequences in more of a calculus perspective. So far, we've really only related this really back to algebra. So we kind of talked about sequences, writing terms of sequences, writing out a general nth term of a sequence. Now I want to talk about a convergent sequence. Okay. Convergent sequence. So if you're wondering, like, well, what does the sequence have anything to do with convergence? Well, think about the types of terms that we've looked at so far. For instance, in example 1, I had you write the first 4 terms of this sequence. Well, what you're looking at here is a bunch of terms for which the quotient gets increasingly small. So you're starting out with 1/2, fine, so 0.5, 0.25, 0.125, and just sort of going through this and noticing that each time the ratio gets smaller and smaller and smaller. So the idea here is to get some sort of sense of, do these numbers eventually converge to a value? Like if I were to follow this sequence out to super large values of n, would I get really, really close to one particular number? That sort of thing. And you could look at this sequence and even say something similar. The difference is that this one oscillates, but it doesn't matter. Notice that in each case, the absolute value is getting smaller. Then if you'd like, we can even graph this in a couple minutes so that you can sort of get a sense of what's happening to this sequence as a function. I think we'll do that. Okay, but for now, I want to give you the definition of a convergent sequence. We're going to let L be a real number. You know what? I'm not going to give you this definition. I'm changing my mind. I'm going to give you a definition that does not include epsilons and deltas because I'm not going to be using them. All right. If the limit as x approaches infinity of f of x exists, then the sequence a sub n, which is, remember, equal to just some function of n, converges to the same limit. So this is actually really good news for you because a lot of your homework here is just going to be a lot of the limits that you worked on more recently in the last chapter. Technically, it was with L'Hopital's rule, which you may or may not need for some of these problems, but you're basically just going to be looking at limits to determine whether or not the sequence is convergent. So if the limit of f of x as x approaches infinity exists, then your sequence is going to have that same limit. If the limit does not exist, remember we usually just would say dne in that case, then we would say that your sequence a sub n diverges. Okay, otherwise your sequence converges. Okay. So we have that. I wanted to give you some properties for these limits because you might find them really helpful as you're working your way through some of these homework problems. I think all of these properties you learned for actual functions when you were in Calc 1, but technically we need to apply them to sequences, and I want to remind you of what they are. So I'm going to give you some properties for limit laws for these sequences. And by the way, these are also on your book on page 578. I'm going to actually just skip to the next page. So this is properties of convergent sequences. All right, so if you have two sequences, S sub n and T sub n, and they are convergent, and if C is a number, move my C over. Are you guys having flashbacks to Calc 1 and being like, oh, I kind of remember this wording? Nobody likes limits. I don't know why. They're really, you know what? Maybe I'll like them more now because I think when you first get into Calc 1 and you start doing limits, people hate them because they're weird. Now at least you have more familiarity with them. You have a much better understanding of how they work. And since you've just gotten through some really grueling stuff in chapters 6 and 7, maybe you'll be like, yeah, you know what? Limits aren't so bad after all. Maybe you'll fall in love with limits. All right. That's what I'm hoping anyway. Gotta find something that you love in every chapter. You're gonna be doing a lot of limits in this chapter. Like every section is limits. Just to warn you. All right, so you have a constant multiple property. I'm not going to write out the names of each. I'm just going to write them out because I feel like it doesn't matter. I mean, you can read them. You pretty much already know these rules anyway, just from applying them to limits, but I just wanted to make sure that we run through them again. Okay, so this means that if you are taking a limit and your sequence is being multiplied by some number c, this is some sort of constant, not a function value, but if you're multiplying by some number c, you can pull that number c outside of the limit. We did this a lot in chapter 7 when we were applying L'Hopital's rule. Technically, it was 4.5. But we did this a lot with the limits where I was like, you know, this is kind of distracting inside the limit, and I would just move it out. It's an option. You don't have to, but you might find that it makes your computation a little bit easier, or sometimes it just sort of clarifies the problem for you, helps you to see things a little bit better. You have a sum and difference property. So this would be if you're adding or subtracting these two sequences. And you know, you're familiar with these for functions. You can add them up, or you can add them together, or you can split them up. So if you're adding and subtracting inside the limit, you can split that up into the sum or difference of two limits if you find that easier to work with. And I think this one, a lot of times we do without even thinking about actually using a property. We just do it. There's one we don't use a ton, and it's the product property, but I just want to make sure we understand that it's available to us. So this is if you're taking the limit of a product of two sequences. That just means that you can just take the product of the limits. You know, the real reason I wanted to make sure to go over these is because one year, a long time ago, like one of the first times I ever taught Calc 2, I forgot to go over these limit properties. And I had a student solve a problem in a really inventive way on his exam. And he even wrote a note on it though after and was like, yeah, I'm pretty sure there's a limit rule that says we can do this, but I don't remember seeing it in my notes and I couldn't find it. And it was because I never went over it. He technically learned it in Calc 1, but I felt really bad then that I didn't go over it because maybe other people would have used it. So that's kind of why I really want to make sure that we're talking about these again. So if you're like, okay, I got it. This is annoying. Sorry. Okay, so you just multiply those limits together. There's also a quotient property, of course. Taking the quotient of S and T just means that you can take the quotient of each of the limits. Of course, this is provided that your denominator is not equal to 0. We can't divide by 0. Okay, so two big ones that we forget about that are actually really, really useful. And actually, it was one of these two that the student that I was just referring to remembered, but I hadn't like reviewed it. So it was one of these two. It's very useful. The second one we're going to use a lot towards the end of the chapter. But this one, we don't use a ton. So this is S of n to the p power. I didn't put parentheses around it because your book didn't, but I might rewrite this one more time just so that's really clear that this is S sub n to the p. What you can do is instead of just applying the power to the function itself, you can apply it to the whole limit. This is one that people always forget about. Now, this will come in handy more often than you might imagine. So if you are making a mental note of this or highlighting it or something, you might be surprised that you would use it more often than you would think. It might make your limit a little bit simpler, because sometimes taking this value to a power really complicates the whole expression. But if you could just find the limit of S sub n and then take the limit to a power, well, usually the limit's just some number that you're taking to a power. It's much simpler to work with. So the last one has to do with radicals, and it's the same idea. This is the pth root of S sub n. And we're going to be using this a lot in section 6. But what this says is that you can take the pth root of the limit. So this one you're going to see a little bit more often, but same sort of idea. This is only valid if p is greater than or equal to 2, because we're thinking about these as being square roots. And S sub n is greater than 0, because that needs to be a real number if p is even. So those are the properties that you can use throughout this section in order to evaluate some of these limits. I'm going to give you a bunch of different examples of limits, and then we'll talk about evaluating them and the different techniques that you might use to evaluate them. I will do that in the next example. Okay. Making sure that this is a comprehensive list of everything I want to do. So this will be example 3. Now, your book is very interesting because it basically has several different sections within your homework, and each section asks you to do the same thing. So I don't know why they have to make it so complicated. But basically, you're just being asked to find the limit of the sequence. I mean, that's really just the heart and soul of it all. Determine if it converges or diverges. If it converges, find its limit. So I'm just going to say to determine the limit of the sequence or show that it diverges. All right. I'm going to be pulling 2 from L'Hopital's rule, which we talked about in the last chapter. It's technically not the last chapter because it was chapter 4, but you know what I'm saying. Last module. I'm going to give you some sequences. I'm going to put them in the same form your book is going to give them to you in. So for instance, for A, we're going to look at n divided by n squared plus 1. This is not the same one that I gave you earlier, but it's similar. It's along those same lines. So if you're trying to determine whether or not your sequence converges, I'm going to go back to this theorem because I feel like it really applies here, and I want to make sure that we revisit it here. If the limit as x approaches infinity exists, then the sequence converges to the same limit. So what we're going to do is we're going to take the limit as n approaches infinity, and we're going to get the limit there. Now, if the limit doesn't exist, then we would say that the sequence diverges. Otherwise, we would say that the sequence converges. So we would find the limit, just whatever that limit value is, would be the limit of the sequence. And some of these, just like with regular old functions, they should make sense to you what the limits are. It shouldn't be some weird value where you're like, well, I don't get it, but okay. And these, you should be able to clearly be able to write out a pattern of numbers here in your sequence and say, okay, like I can see how it would head to this value. If it's a value like E, it's not as easy to see that. But if it's heading to 0, that's something where you should be able to see each one of those terms get closer to 0. All right, determine the limit of the sequence or show that it diverges. Our first one is n over n squared plus 1. So we're going to take the limit as n approaches infinity of n over n squared plus 1. Now, technically, we have a situation here where we have infinity over infinity, but that's fine. You don't have to show me that you have an indeterminate form. If it's very clear to you that you have a situation where you have an indeterminate form, feel free to just use L'Hopital's rule. You don't have to write like, I'm using L'Hopital's rule here. I'll know what you're doing. Take the derivative in the numerator and the denominator to rewrite your function. And remember that only works if you have an indeterminate form when you evaluate the limit. And now we have a constant in the numerator, so we don't have to worry about an indeterminate form anymore. And when we divide by infinity, our ratio is going to go to 0. So constant divided by infinity runs its course up to 0. And this is one where, I mean, we're not going to do this for every single one, but you can get a sense for what's happening to this if you were to write out the terms of your sequence. So if you're thinking about, for instance, well, n equals 1 is a half, n equals 2, 2/5, n equals 3, n equals 4. Wait, is this the same one that I gave you before? I could have sworn I checked and it was different, but oh no, I gave you an oscillating variation for example 1b. But yeah, same values. And we sort of discussed already when we were going through example 1b that the absolute value of these numbers was getting increasingly smaller and smaller. The ratios were all decreasing. So just by looking at the first 4, for instance, terms of your sequence, you can see that these values are getting smaller and smaller. The denominators are growing much more rapidly than the numerators. And I sort of want you to get used to thinking about things that way. If the denominator is growing faster than the numerator, then it must be the case that eventually you're going to get to a situation where your ratio is going to go to 0, which is what we see here. Okay, let's do some more of these, because like I said, you're gonna have a ton of these for your homework, just finding these limits. The next one will be 4n cubed divided by n cubed plus 1. Okay. I was thinking, like, I just gave you guys these rules for rational functions and their degrees and what happens as n gets increasingly large. But I just remembered that it was summer calc 1 when we were talking about that, and we were talking about limits and infinity. So I did not recently give you those. If you remember the rule from algebra that says that if the degree in the numerator and the denominator is the same, then the limit as n approaches infinity must be the ratio of the lead coefficients. That's fine. 4 over 1 is 4. That's going to be the value of your limit. Otherwise, I'm not going to go through and give that to you again. You can easily use L'Hopital's rule to figure this out for rational functions. So you have infinity over infinity. But then again, I'm going to move left a little bit because we might have to do more iterations of this. You're going to get 12n squared divided by 3n squared. And then you're going to simplify that again, and you'll get 24n divided by 6n, which is 24 divided by 6, which is 4. Now, if you don't believe me, of course you believe me. Why wouldn't you believe me? But I mean, think about what this would actually look like on the graph. And maybe for a function like this, it's really hard to consider that. You will have 4x cubed. Don't enter n here. Keep your variable as x. All you need is just a picture of the graph. and x cubed plus 1 in the denominator. Don't forget your parentheses. Do I need to start with the crazy light? It's getting dark outside. Doing my asynchronous lecture at a weird time of the day. My children are napping. I don't know. Okay. So there's your function. I can't remember. Darker. It's all the way dark. Okay. Yeah, because lighter just makes it disappear. Okay. You can graph this. Maybe zoom standard. Oh, yikes! Did I hit the wrong button? I did. Zoom standard. And actually, maybe even zoom standard wasn't the best choice because we're only thinking about this function in terms of values of x that are greater than 0, or I should say greater than or equal to 1. So if you'd like, you can change your window so that your x min is 1. That's the smallest x value for the domain that you're going to have. And then you can graph it again. Now, I think it's kind of helpful that we saw the whole graph at first, otherwise this might look kind of confusing, but you can see that these values really do level off to 4. And if you start to look at your table for values of n that get increasingly large, your calculator is going to round them to 4 anyway. That one it just gave up on. So you can kind of see that it works the same way. Oh, I should mention the only difference here between your function and your sequence is that for the sequence, you're only plotting values of in your domain that are positive integers. So this function has values in the domain that are, cover the whole domain of values, basically your whole real number system. But for you would just be looking at a series of dots for what's happening as you work your way through. So if I were to go to my table, for instance, and I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, these would be the values that are actually being represented by my sequence. So I would, of course, have to turn those into fractions, but the first term of my sequence would be 2. The second term would be 3.5556, 3.8571, so on and so forth. Now, of course, these are just the decimal variations of the values in the ratio, but you can see now what's happening to the terms of this sequence. And just continue to head towards 4. So we would say that this converges. Also, sorry, we didn't specify, but we should say, for example, A, we should have said converges. I mean, you probably got that, but just want to make sure. Converges. Excellent. So I just want to go through some limits here that I thought you might possibly get stuck on. Something like this is one that students get stuck on. 3n divided by the square root of n squared minus 1. The reason students tend to get stuck on this is because anytime there's a radical involved and you try to use L'Hopital's rule, you end up in a weird position where you just end up moving that radical from top to bottom, top to bottom, top to bottom, and usually you end up not being able to simplify it out. So I want to show you a technique for how to deal with this situation. What I mean is I should probably try to use L'Hopital's rule on it so I can show you what happens. It might not happen in this one, but I want to show you a general technique for if it were to occur. All right, so you would get the square root of infinity squared, which is still technically infinity in the denominator. Okay, so if you arrived at this conclusion and you were like, okay, cool, I'm going to use L'Hopital's rule, no big deal, that's fine. You would take the derivative in the numerator. And when you take the derivative in the denominator, remember you've got a situation where you have n squared minus 1 to the 1/2 power. So you would take 1/2 times n squared minus 1 to the negative half, and then you would multiply it by the derivative of the inside function. Well, this is where the issue occurs here. So when you rewrite this, you would bring the square root up, and technically if you're dividing by a half, you're multiplying by 2, so you could bring that up also. So the negative exponent, you'll move that expression into the numerator. Well, now look what happened. Now you still have an n in your denominator. So if you were to apply L'Hopital's rule again, you'd see the same thing happen. You'd see this switch, and it would just keep going on and on and on and on. And you're going to find that L'Hopital's rule will fail you in this instance. So that happens very often with radicals. So I'm going to show you a workaround for this. It shows up surprisingly more often than you might imagine. So we will take the limit as n approaches infinity. I guess technically maybe I should have rewritten this before we put the limit on. I know that students don't like to keep rewriting the limit, but what you're going to do is you're going to divide by the n that's in both the numerator and the denominator. So you're going to take the 3n in the numerator and divide by n. And you're going to do the same thing in the denominator. Now, remember, I'm going to write this out twice, actually, so it's really, really clear. N squared minus 1 divided by n. So I haven't changed anything at this point. And whether I multiply both the numerator and denominator by a value or divide them both by a value, as long as I've done that operation to both the numerator and the denominator, I haven't changed anything. So when we rewrite this, I'm going to simplify this inside the numerator. So the whole point is I want to get this inside my radical so that I can simplify what's underneath the radical and take the limit of my simplified expression without having to worry about infinity. I'm trying to eliminate the infinity that was happening here when we were taking the limit. So in the numerator, I'm going to get 3. And the denominator, I'm going to write this as the square root of n squared minus 1. And then we can rewrite n as the square root of n squared. Right? It's like the square root and the square sort of cancel each other out. So if I rewrite the n inside the radical, then I need to apply an exponent of 2 on it. And if you're wondering, well, how does this help? Split up your denominator now inside your radical. So we're going to rewrite this as the square root of n squared over n squared minus 1 over n squared. And now you can see that this is actually really good, because now you'll notice you have the limit as n approaches infinity of 3 divided by the square root of 1 minus 1 over n squared. This is good because now I can take the limit without having to worry about an indeterminate form. First of all, I have a constant in the numerator. That's really what we're going for here. So I don't need to worry about an indeterminate form. We created the constant in the numerator by just dividing out the variable, but we had to deal with it in the denominator. But now we've done that. And we've created this really nice situation where in the denominator, we have a constant divided by infinity, which is going to zero out. So the square root of 1 minus 0 is the square root of 1. And your limit is 3. So in this case, we would say that the sequence converges to 3. And the nice thing is, at least you can put this into your calculator and, just check and make sure that that makes sense. See that for really large values of n, the y values will head towards 3. So this example is really important. This technique you're going to see throughout the chapter. I don't want to see you do a bunch of crazy stuff that is technically mathematically illegal just because you don't know of a workaround. I say this from experience. I see students do all kinds of crazy things that are not valid. Okay, D. So this is sort of a weird one. Weird, but not weird, because you're going to see this type of example where you're being asked to find this limit. For something like this, actually applying the limit is not really going to work for you. If you were to write this as the limit as n approaches infinity of cosine n pi, you'd be like, okay, how does this make sense? Because the cosine of infinity is what? And then you'd be stuck. So if I were you, I wouldn't think about it like this. I would start to, for some of these weird ones where you really can't take the limit, I would write out some terms and see if you can get a good sense for what's happening. So for instance, if n equals 1, you'll have cosine pi. If n equals 2, you'll have cosine 2 pi. N equals 3, cosine 3 pi. Cosine 4 pi. So on and so forth. So the cosine of pi is -1. The cosine of 2 pi is +1. The cosine of 3 pi is -1. The cosine of 4 pi is +1. You can see now what's going to happen with these terms. Are you ever going to see an instance where this value is anything other than plus or minus 1? No, because all you're doing is just flipping back and forth between this value and that value. And as long as you're looking at, okay, pi, 2 pi, 3 pi, 4 pi, 5 pi, oh, sorry, 6 pi, 7 pi, you're constantly just going to be going back and forth in between these cosine values. The cosine is the x value at these points. Think about your unit circle. No matter what, these values are not going to stray from this pattern. Therefore, they don't actually converge to a value. You could say that the sequence diverges. The limit does not exist. The values oscillate between plus or minus 1. I mean, really, if all you're being asked to do is state whether the sequence converges or diverges, and if it converges, find the limit, that's fine. For something like this, I mean, on a test, yeah, if you just wrote diverges, I'd be looking for some work, and I'd be like, okay, why? Like, give me a reason why. But on your homework, it'll just be diverges. All right, let's see what else I have in store for you. Okay, so we talked about this oscillating sequence. Let's talk about another oscillating sequence. This one is going to even look oscillating. Just by the look of it, you're going to tell that it's an oscillating sequence. Okay. This is -1 to the nth power divided by n squared plus 1. Trying to figure out if there's a theorem for this one in your book. I don't think there is a theorem. Unfortunately, there's actually not a theorem for a lot of these things. It's just kind of, a lot of this is you using your common sense and being able to come up with solutions. Okay, so you are looking for the limit as n approaches infinity of -1 to the nth divided by n squared plus 1. Now, this is another one where you can't really write the limit because you'd be writing this as -1 to the infinity. But so I'm gonna do something that's a little bit informal. Okay. I want you to think about what happens always to the numerator. If n is 1, the numerator is going to be -1. If n is 2, the numerator is +1. -1, +1, -1, +1. It's going to do that all the time. And then what's going to happen is in the denominator, if you were to actually apply this limit, you would see that the value in the denominator would head off towards infinity. So infinity squared is also known as infinity. And I know, sorry, this is terrible notation. It's terrible. I hate writing it. But I think this is the easiest way to see this one. You've got always some sort of constant. Now, it does not matter that it's not the same constant, that it oscillates back and forth. The fact of the matter is the numerator is always constant, and the denominator, it gets increasingly large, sending that ratio off to 0. So you actually have a situation where your limit is 0. Maybe we can look at this in our calculators. Let's see. There is a way to plot this so that you just see ... It's been a while since I've done it, though. It's probably really simple, and I just forgot it. It's like out of my mind. -1 to the x power divided by x squared plus 1. And remember, we originally had this set up to only work for values of x, so starting with an x min of 1. So we can keep it that way. What is happening? All right, let me look at the values here. If n is 1, we should be getting -0.5. If n is 2, did I confuse my calculator? I don't know. All right, maybe it's confused, or I just entered it funny. All right, I'll leave it with some positive values, which really doesn't illustrate what we're trying to get it to do here. Okay, but you can see no matter what, that whether or not the numerator is jumping, these values are going to sort of just like, it's hard to see. They're just going to stay really close into the x-axis. And you know what? I think we could also just look at this by hand if you wanted to do that also. Let's see. I don't know why my calculator does not like that. But I mean, if you were to think about what this would look like if I were to graph it by hand, for n equals 1, you would have 1 squared plus 1 is 2 in the denominator. You'd have -0.5, so it'd be like right down here. If you had your second term, you'd be at 2 squared, which is 4, plus 1 is 5, positive 1/5. So these are going to head into the x-axis really rapidly. If we had n equals 3, 3 squared plus 1 is 10. So you'd have -1/10. So you'd be below the x-axis, but barely. If n was 4, I should have actually spread these out further, but that's okay. You'd have positive 1/17. So again, even closer. I mean, it's like I can't even draw it at that point. So you'd be getting the situation where now you're boop, bop, boop, bop, boop on each side of the axis, but each time all these little boop, bop, beeps are getting even closer and closer to the x-axis. That's what you would see when something's converging. Converges to 0. If you had a situation where the values were diverging, you might see, if it was oscillating, you would see the boop, bop, boop, but then you'd see them get further and further and further away from the x-axis. That'd be a very different situation that you'd have on your hands. All right, I'm going to remind you of something that you did very recently. If you took your exam and did this on your test, this will be 5 plus n over n to the nth power. Oh, you know what? I forgot my parentheses. Okay. So go ahead and take your limit as n approaches infinity of 5 plus n over n to the nth power. Okay. So this is the type of thing that we saw in 4.5 when we were talking about L'Hopital's rule. We were saying, well, we really are going to have a hard time taking this limit the way that it's written because we have a variable in the exponent. If you'd like, you might find it to be a little bit more straightforward to write this as 5 over n plus 1 to the nth. It does not matter, but since I know that at some point I'm going to need to use L'Hopital's rule, I would rather take a derivative of this than use the quotient rule on that, but probably doesn't make much difference. It's probably neither here nor there. Set that equal to y. What we need to do is we need to get this variable out of the exponent. We're going to do that by applying a natural logarithm. So the natural log of our limit y is going to be equal to the limit as n approaches infinity of the natural log of 5 over n plus 1 to the nth power, which is going to be the same as take the n out front and then take the natural log of 5 over n plus 1. Okay, now if you'd like, you can still try to take the limit here. If it was indeterminate before, I mean, you didn't cancel anything out, you didn't get rid of anything. At this point, it's still going to be indeterminate. If you're setting n out to infinity, 5 over infinity goes to 0. The natural log of 1 is negative infinity. Or I'm sorry, the natural log of 1 is 0. I was thinking natural log 0. But the natural log of 1 is 0, and here would give you infinity. So this would be infinity times 0, in case you needed extra convincing. We didn't show it here, by the way, but this is like infinity over infinity to the infinity. So this was like a nightmare. Okay, so let's go through the rest of this and use L'Hopital's rule here. Go ahead and rewrite this as a quotient. The natural log is going to have to stay where it is. If you'd like, since you know you're going to have to take the derivative, you might want to write that as n to the negative first. I don't know. I might regret that. When you move the n into the denominator, again, you know you're going to have to take the derivative. You can write it as n to the negative first. If you move its position in the fraction, you switch the sign on the exponent. And then you take the derivative and reapply the limit. So for your natural log, your derivative is going to be u prime over u. So the derivative of the inside function divided by the inside function. So negative 5n to the negative second divided by 5n to the negative first plus 1. Divide that by negative n to the negative second. Now, to simplify this, if I were you, I would probably rewrite this back as fractions, which is going to be super crazy because you're going to have a lot of them. So if you'd like, maybe before you do that, deal with your complex fraction. Technically in the denominator, this is written over 1, if you want to think about it like that. When you're dividing two fractions, you multiply by the reciprocal. So if you're multiplying by the reciprocal, then you're multiplying by 1 over negative n to the negative second power. Some of you just get used to realizing that you multiply this into the denominator also. I'll leave that up to you. And since you have the same factor here in the numerator and denominator, if you'd like, you can go ahead and cancel that out. You can even cancel out the negative if you'd like. Don't cancel out the 5s though, whatever you do. Can't cancel those because this is not it's not a factor at this point, it's a term. But you still have a 5 in the numerator, and in the denominator you have 5 over n plus 1. Now this is nice because in this situation, now you're in a spot where you can apply the limit and you won't need to worry about getting in a determinant form. So you'll have 5 divided by 0 plus 1, which is 5. And don't put a box around it. That's not your answer. Remember we said that y was equal to, or sorry, not y, the natural log of y. Yikes. I was about to botch this. Okay, I'll write it this way. ln y equals 5. And y was, remember, our limit. So that must mean y equals e to the 5th. So same idea from the last unit we were in, just applied to sequences. G, yeah, I've got more. I'm just going to keep going. This one I really like, though, because I feel like it's very instructive. I like all of them, but for different reasons. This is the limit as n approaches infinity of, if you want to leave the n to the 10th in the numerator and move e to the n to the e to the nth power to the denominator, that's fine. Just switch your exponent and make it positive, since you've changed its position in the fraction. Okay, now I want to tell you something about growth rates, because I really want you to understand how the growth of a function is going to affect your limit, because I don't want you to feel like, oh, do I really have to take this derivative 10 times? Okay, I mean, officially, yeah, you can say that eventually this guy is going to go down to a constant, and then it's going to go down to 0. The e to the n, its derivative will always be e to the n. So at some point, you're going to have 0 divided by e to the n. But as far as growth rates are concerned, there's kind of like a list of growth rates here. The first one is a natural log function, and it could be like the natural log to some power. This function grows really slowly. Now, to denote the growth, I'm just going to put these little arrows here. I'm going to say this one grows way more slowly than, for instance, n to the p, where p is just some power. So that would be a situation like what you have here. Then you have a situation where you could have b to the nth power. So this is some real numbered base, and n's your variable. So this one is going to grow a little bit faster. You know, it's like if you're taking, for instance, e to the n, or like 10 to the n or something. Your base is real. Your exponent is up here in the variable. I'm sorry, your variable is here in the exponent. What am I saying? What moves even more quickly than that is a factorial. So n factorial gets really large really fast. I mean, think about what happens if 1 times 2 times 3 times 4 times 5 times 6. Those numbers get really, really big really quickly. And then what grows even faster than that is n to the nth power. So some sort of value taken to its own power. So, you know, you could potentially have like 1,000,000 to the 1,000,000th power and even larger. So this is something to keep in mind as you go through here. And if you're ever going to use this to consider what's happening with your limit, just justify it by just telling me that, for instance, e to the n grows faster. If you said that and then told me what the limit was, fine. You're taking something that grows a little more slowly and you're dividing it by something that gets really big really fast. If the denominator is getting big, the quotient is getting small. We could say that in this case, our limit would be heading off to 0. If you didn't feel comfortable doing that, you could, of course, use L'Hopital's rule a couple iterations in, and you'd be like, okay, this is enough. I've seen enough. This is just going to be a situation where I'm taking the derivative over and over, and eventually this is going to go down to a constant, and eventually it's going to go down to 0. So something to consider. Now I'm going to remind you of something that you learned also in Calc 1. Hold on one second. So sorry, that was weird dead time right there. Okay, I'm going to remind you of a Calc 1 thing. Sorry, I'm having this kid not napping situation. Technically, he needs to wake up, and my husband's not here. Sorry. He's fine. He's going to go play Nintendo. My kids love video games. Okay. Oh, you know what? I said I was going to put these in braces for you. So I want to put this in braces so we can keep our notation consistent. Same idea, just with braces. It's the same notation means the same thing. Okay. This is another one where you can sort of think about this using what I did a few examples ago. You could write out the limit and then say, okay, sine 6n over 5n. And then you could think about this as being like, okay, well, sine of, and then as n keeps getting increasingly large, so let's say n was 1, you'd have sine 6. If n is 2, sine 12. But remember what happens with your sine function. As it goes around the unit circle, it's going to start out positive, and then it's going to become negative, and then it starts again positive to negative. And it's going to have this behavior where it's going to oscillate its value. You learned in trig that the sine function always has a value between -1 and +1. So you can even say that between -1 and 1, whatever it is, whatever the numerator is, it can't be any bigger than 1, and it can't be any less than -1. It just can't be. That would be outside of the range of the sine function. Now, in your denominator, however, when you send n off to infinity, your denominator goes to infinity. Well, now you're taking a constant and dividing it by infinity, and your ratio is going to go off to 0. And you know what? I was going to remind you of the squeeze theorem. I'm going to do it just because it's never a bad thing. So the squeeze theorem is another tool that you have available to you. You learned it in Calc 1, but basically what the squeeze theorem did was it said that you could set up your function and squeeze it in between two different functions whose limits you know. And if those limits on the outside match, then it must be the case that your function has the same limit. So I'm going to show you, and when I do, you'll be like, oh yeah, I remember doing that. So what you can say is that the sine of 6n has to be between -1 and 1. Now what you're going to do at that point is you're going to create your function from that function. So if that's true, I'm writing this again because it's important that you see the whole thing. I can create my function by dividing by 5n in all three parts of the inequality. So to use the squeeze theorem, you start out with something you know. that relates to your function, and then you build your function. And if the limits of if the lower limit and the upper limits match, then you have a situation where you can conclude that the limit of the function in the middle must be the same. So we could say then that the limit as n approaches infinity of -1 divided by 5n is 0. And the limit as n approaches infinity of +1 over 5n is also 0. Therefore, the limit as n approaches infinity of sine 6n over 5n equals 0 by the squeeze theorem. Some of you will like this just because you don't like to do weird stuff like this, because it's weird. I don't like doing weird stuff like this. I mean, some of you love it because some of you are very logical and you just are like, okay, well, yeah, this makes sense because, and then you kind of write it out that way. Others feel like they need to justify everything with something that's precise and mathematical. If you're one of those people, use the squeeze theorem. So that was from Calc 1. Okay, let's see. One type of sequence that you would see where the limit is not quite as obvious, might be obvious to some of you. Everybody's different. Everybody's weird in this chapter. When I was a Calc 2 student, I shouldn't say this. I hated this chapter. I had the hardest time with it. I mean, if you told me to integrate something, I could do it. Even the applications of integration, awesome. But when I got to this chapter, I was so confused. It was just a different way of thinking for me. And it wasn't until I got into grad school that I really got to be more comfortable with talking about sequences and series. Okay. Oh, I did it again. Sorry. All my examples are written like this. But I want to match your text. So I want to switch my notation. Okay. When you see something like this, remember that there's a rule from algebra that said that if you are taking a ratio to a power, you can take both pieces of that ratio and take it to that power also. So from algebra, you learned that a over b to the nth power was a to the n over b to the n. You might not use that a lot, but you're actually going to use that quite a bit in this chapter because we're going to be writing things that are in this form. So if you have a hard time thinking about it like this, because, think about it, you're going to be taking this limit and you're going to do this and you're going to be like, okay, great, infinity over infinity. You might find it more helpful if you write it as 4/3 to the nth power. So we could say that this is equivalent to writing that quotient 4/3 to the nth power, the whole thing. Now, when you do that, again, this is not the most straightforward thing. But what you're going to find is because this ratio inside that's being taken to the nth power is greater than 1, your limit's actually going to be infinity. So your terms are going 4/3, 16/9, 4 cubed is 64, 3 cubed is 27. 64, I don't remember. 64. 256. Oh, I should have remembered that. Over 81. 4 to the 5th is what? 1024. Okay. 1024 over 3 to the 5th is 243, right? 243. Notice that in this case, your fractions started out such that these numbers were pretty close together, 3 and 4, only 1 unit apart. But as you moved from one term to the next, the ratio here is getting bigger. It's not that it's going to 0, it's the opposite. 16/9, well, now you're separated by 7. 27 and 64 are separated by a lot. And then these numbers are going to continue to get further apart. So these ratios keep getting continually large. And so as you see this behavior where the ratios are getting increasingly large for each successive term, we can say that this limit must be infinity. So if you remember that if this value, if this number is greater than 1, then the limit as n approaches infinity will be infinity. But if the number is less than 1, then the limit as n approaches infinity will be 0. Because in that case, you'd be taking, like 1/3 to the n or something like that, or 2/3 to the n. And in each case, that ratio would keep getting smaller and smaller and smaller in each successive term, because the denominator would grow more rapidly instead of the numerator. Okay. Let's see. I have I, J, K. Oh, I wanted to do one. The special form. There we go. So this is a sub n equals, guys, I did it again. If you wrote a sub n, it's not a big deal. Minus ln n plus 1. All right, so there's your sequence. I want to remind you of some properties for natural logarithms. If you are taking the difference of two natural logs, you can write that as the logarithm of a quotient. So if I were you, I would do that. Notice, by the way, that if you tried to take the limit here, because if you're like, well, why would I have to do that? You would get infinity minus infinity, which is not a good situation to be in. If you were to write it like this, however, you might still think this is terrible because the natural log of infinity over infinity is still indeterminate. Remember, though, that we can move that natural log outside of the limit. We've only really put it inside, but let's say that we rewrote this as the natural log of the limit as n approaches infinity of n over n plus 1. Well, this is a much easier problem. Now you're not in some weird situation where you have to use the quotient rule and try to, actually you'd be stuck here. You wouldn't even be able to write that as a quotient. Write it like this, and then you can take the limit inside and then take the natural log of that limit. So you can use L'Hopital's here if you'd like, unless you remember that rule from algebra. Some of you are going to pop into my office hour and ask me about it now. But it would just be 1 over 1 if you were using L'Hopital's rule. And then this would be the natural log of the limit as n approaches infinity of 1. And the limit of a constant is the constant itself. So you'd be looking at the natural log of 1, which is 0. So bear in mind that you can work your natural log inside and outside of your limit. And then I have one more of this type of example for you. And then I also wanted to cover what it means for a function to be bounded. So this one is the inverse tangent of the square root of 3 plus 4 over n. Okay, so we can take the limit as n approaches infinity, and we're going to apply the same thing here. Instead of actually taking the limit of the inverse tangent of the square root of 3 plus 4 over n as n approaches infinity, we can apply the inverse tangent to the limit. So just this whole idea of being able to move this limit inside and outside of the function. I know that really wasn't in one of your properties, which is why I want to show it. It's a general rule, but it was not specifically stated as one of your properties. So we'll take the inverse tangent of the limit as n approaches infinity of this function. And this is going to be the inverse tangent of the square root of 3. And then the limit as n approaches infinity of 4 over n is 0. And then you just have to remember how to find the inverse tangent of the square root of 3. So you're asking yourself, the tangent of what angle is the square root of 3? And I'm going to tell you it's pi over 3. Because I remember, even if you don't. If it's pi over 6, then that's root 3 over 3, the more complicated one. I don't know. That's always the way I think about it. Okay. 1 second. All right. Sorry about that. So many interruptions today. Okay, so the last thing I wanted to talk about was being bounded and monotonic, and whether or not a sequence is bounded or monotonic has a lot to do with whether or not it will converge. So I'm going to give you some rules about that. Oh, you know what? I just realized. Oh no, never mind. I thought there was this theorem that I was looking for. I was like, I wish they had a theorem for that. And then I thought that it was in here. But now, never mind, it's not in here. Oh, no, it is in here. No, this is it. This is it. I'm going to give it to you real quick. I did not notice it before with this particular book. I don't know why. I somehow glossed over it. Let your nth partials, let your S sub n be a sequence of real numbers. If the limit as n approaches infinity of S sub n equals L, and if f is a function that is continuous at L and is defined for all numbers S sub n, then here's what we've been using the last two examples. The limit as n approaches infinity of f of S sub n is equal to f of L. Basically just stating that you can move this function in and outside of the limit. So if your limit is equal to L, then you can just apply the function to that limit. So this was used in examples J and K. But that was what we used. We basically just said, okay, well, we have this function. We're going to move it outside of the limit. Now, technically, there were some conditions we were supposed to check. I mean, I just know that for these functions, that's going to work in these cases. But I wanted to make sure I gave you the theorem that stated that, just because I mentioned it. Okay, let's talk then about what it means to be bounded as a sequence. Okay. Let's see. Squeeze theorem we talked about. Yes. All right. Boundedness. All right. Theorem. Boundedness theorem. Okay. A convergent sequence is bounded. It's probably the shortest theorem I've ever given you. A convergent sequence is bounded. It started out so quiet, and now the piano's going and the crying is happening. I'm going to wrap this up soon, you guys. No worries. Don't worry about it. All right. The theorem that sort of goes along with this is a test for divergence of a sequence. Test for divergence of a sequence. If a sequence is not bounded from above, and we're going to talk too about what it means to actually be bounded, like what that looks like on your function. If a sequence is not bounded from above, or if it is not bounded from below, then it diverges. Now, the way that your book states this, I don't think is that great. So I want to make sure that we put a little caveat onto this. This is kind of the unfortunate thing about having taught this out of so many different books. Everyone's got a different way of writing things. All right, a convergent sequence is bounded. I don't know. That's fine. But basically, a sequence, I'm going to say this in my own words. Must be bounded from above and below to converge. Now, that does not mean that every bounded sequence converges. It's just saying that if a sequence does converge, it must be the case that it's bounded. But you could have a sequence that's bounded, but it doesn't converge. So the best way for me to show you what it means to be bounded is graphically. So if I'm thinking about, for instance, looking at a bounded sequence, I might be looking at something like this, where I start out here at n equals 1. My values start out maybe they're oscillating, but we're in a situation where they get closer and closer and closer to the x-axis. So the values get closer and closer to 0. So this would be an example of what a bounded sequence would look like. It doesn't have to look like this, but the goal is that you can figure out an upper limit and a lower limit for which all your values are going to lie between. So maybe this would be your lower limit and your upper limit. My husband is home, by the way, in case anyone's worried that I just have crying children running around by themselves. He's handling it. Okay, so if you can find these two limits that enclose your sequence, then this is really what it means to be bounded. So I kind of want you to have this visual where you're seeing that, okay, all these data points that are inside my sequence, they're bounded above by some number, don't know what it is. Maybe you do know what it is, and then bounded below by another value. Now, a sequence that would not be bounded, okay, so this one is bounded. Something that would be not bounded, you can probably guess what it's going to look like. But maybe I have values that start out, and maybe they're oscillating, maybe they're not. We could just have them get only larger, but have them get only smaller. But let's say maybe they get increasingly further away as n gets increasingly large. And that's problematic because, I mean, yeah, even though technically I can technically draw lines that would bind them. Remember that n's going to keep getting larger. And as n keeps getting larger, these values will continue to get big, and they're going to oscillate more and more and more and more. And you're seeing that behavior now where I actually won't be able to say, okay, well, this is my upper limit. Here's my lower limit. It's not going to work that way. So that's the difference between bounded and not bounded. Now, of course, these are just examples that I think are the easiest way to see the concept, but it could be an infinite number of examples. The case for bounded and not convergent, see, we might want to even specify that this one is bounded and convergent. Of course, if you're not bounded, you can't be convergent, so we don't even have to worry. This, of course, diverges. It must. Would be a case where we have this oscillating. Remember, we had situations where the numerator, or maybe the function value, like that cosine n pi, just went back and forth between plus and minus 1. So you might just have these values that, yeah, they're bounded. It goes from +1 to -1 to +1 to -1. And we don't have to worry about them going outside of those bounds. However, this does not converge to a value. We can't see that the data points are at some point going to zero in somewhere. Maybe not zero in, maybe that's not the best word, but we're not getting to some place where we can see that the values are heading into one specific value. So this one would be, that oscillating function, which is bounded, diverges. And if it's easier to think about that as not convergent, think about it that way. If you have an easier time thinking about this as a function where you see the oscillation, think about it that way. I mean, technically, we don't have data points existing in between n equals 1, n equals 2, and n equals 3, and n equals 4. But sometimes just getting that visual is helpful. So I want you to understand the difference. So this one is bounded, but it doesn't converge to a value. So it diverges. Limit does not exist. Here we have the limit exists. This one, we can't say. We just know it diverges. The limit doesn't exist. It goes off to plus or minus infinity. Okay, so that is bounded. I mean, your book does mention monotonic. I just don't want you to be shocked on the homework. So monotonic, I'll give you a definition. You can't talk about sequences without at least defining what it means to be monotonic and bounded. Key here. All right, so the definition, and on your book, it's on page 584. It's actually, I think this is a pretty good definition. A sequence is said to be the sequence is, of course, S sub n. Increasing. So there are a bunch of different definitions here. And by the way, don't be like, okay, increasing, got it. I'm going to tell you what the difference here is between increasing and non-decreasing. They're not the same. So this is increasing if S sub n is less than S sub n plus 1 for n being greater than or equal to 1. So that would be increasing. Now, there's the difference, and I'm going to show you what that is between increasing and non-decreasing. So increasing means the values are going up. Non-decreasing just means they're not going down. It doesn't mean that they're going up. It doesn't mean that they're going down. It just means that they're not going down. Did I say that wrong? Increasing means they're going up. Non-decreasing just means they're not going down. So if S sub n is less than or equal to S sub n plus 1, for n being greater than or equal to 1. So it could be the case that, you know, your terms in your sequence go 1, 1, 2, 2, 3, 3, something like that. Or maybe they're even just 1, 2, 2, 2, 2, 2. I don't something. It doesn't matter. I mean, they could be 1 all the time, and they could technically be non-decreasing. 1, 1, 1, 1, 1. I mean, they're equal, so that's all that matters. Whether they're increasing or not, it doesn't matter. They're non-decreasing. They are decreasing, however, and now you're starting to get a little bit more of a sense for this, I think. If S sub n is greater than S sub n plus 1 for n greater than or equal to 1. So if your terms start to get smaller, then they're decreasing. Then we also have non-increasing, which doesn't mean they're getting smaller. It just means they're not getting larger. Okay. Like that. If any of the above conditions hold, the sequence is called monotonic. Oh, monotonic. Now, I'm not going to do a whole ton with this because in order to show in a lot of cases that your sequence is decreasing, sometimes you can eyeball it, and other times you actually have to apply the first derivative test and test the first derivative and just show that it's decreasing. I might show you an example of that, but I don't want to get too carried away. But I want to just talk a little bit about bounded and monotonic so that you've seen it. And then we'll call it a day. Let's see. Let us see. Determine if the sequence is bounded and or monotonic. Will be our last example. I want to say it's example 4. Determine if S sub n is bounded and or monotonic. So there will be a couple of problems on your homework that cover this, but not a ton, just a little bit to sort of get your feet wet. The nice thing is, like I said, if you can show that your sequence is bounded and monotonic, that it converges. Where's that theorem? It should be a theorem in your book. I know the theorem. Where is it? I must have missed it. It's because it's worded funny. Okay. That's fine. I'll give it to you right now. Theorem. An increasing or non-decreasing sequence that is bounded from above converges. This has a second part to it. A decreasing or non-increasing sequence that is bounded from below converges. so you can get a visual on this. Okay, so if you have an increasing sequence, so the terms are getting larger, but it's bounded from above. So maybe that would look something like this, so that like, yeah, technically the terms are increasing, but maybe they're starting to increase less rapidly. And you can actually find this limit. Sorry, I should make this a little bit darker. Then you can say at that point that the sequence would converge. So as long as it's increasing or not decreasing and it's bounded from above, we can conclude that it's convergent. Same idea if it's decreasing and bounded from below. So it might be doing something like this, but as long as we know that it's bounded somewhere from below, and it could even be lower than this, we would say that it would also have to converge in that case. It must be the case. So that's kind of how that theorem works. Just, I gave you just sort of a quick example to illustrate that. I think sometimes I hate to give generic examples, but I think with this particular section, it's helpful for students. Okay, so we were on example 4. I'll just give you a couple of examples and we'll be done. The instructions were to determine whether your sequence was bounded and or monotonic. Let's do, first of all, -4/5 to the n. And sometimes with these, it's helpful just to write out some terms and get a good sense for what's actually happening with your terms. Yes, you could also think about this in terms of a limit, and thinking about the fact that this ratio is less than 1. Therefore, you should see this ratio getting smaller and smaller and smaller. You could think about that also. But the first term would be -4/5. The second term, when you square this, is going to be positive. Now, that's okay. Maybe not for being monotonic, but as far as being convergent and bounded, fine. Should be good. So when you square this, you get 16/25 cubit, and you get -64 over 125 to the 4th, positive 256 over 625, right? Am I doing 5 to the 4th wrong? No, I don't know why I thought I was. Negative, and then 1024 divided by, I don't remember, 5 to the 5th is 3125. All right, so notice that you started off with this fraction that was kind of close to 1. You got 0.8. But now when you're done here, you end up, well, you're not done, but once you get even to this 5th term, now you're looking at something that's getting significantly smaller. It's a little bit close to 1/3. Now, it's not monotonic because you're noticing that the sign continues to change. It's oscillating from negative to positive, negative to positive. So it's not monotonic. However, we could say that it's bounded and if you were thinking about this in terms of, I don't know, let's say you're at like -0.8-ish, and then you get to be a little bit like this. So you're kind of doing something like that. This value right here was the -4/5. That one was 16/25. And that's as high and as low as you go. Bounded from above and below. I don't think they're asking you about specific values that bind. No, the instructions will just be determined whether it's bounded from above, bounded from below, both, or neither. So this would be both, bounded from above and below. And then you'll also be asked to determine whether the sequence is monotonic. If it is it increasing, non-decreasing, decreasing, or non-increasing? So we already said it's not monotonic, and it's both bounded from above and below. So if you're sort of thinking about how to apply these new terms, that's the way that we would do it. Let's see. maybe we'll do a trig one. This one will be the sine of n pi divided by 2n. Now, again, I think it would be most helpful here to sort of think about what terms you're actually seeing inside the sequence. So if n equals 1, the sine of pi is 0 divided by, in our case, 2. So 0 divided by 2 is 0. If n is 2, the sine of 2 pi is also 0. If n is 3, the sine of 3 pi is 0. Weird, right? Okay, so you're just looking at 0, 0, 0. And some students would find this very tricky because they're like, is it bounded? Is it monotonic? It's actually both. It's monotonic because it is non-decreasing and it's non-increasing. Yes, so we don't need to worry about that. So we can say it's monotonic. In this case, I wonder if they're going to give you options to choose multiple things. It's non-decreasing and it's non-increasing. We'll have to see how Achieve handles this. Non-increasing, sorry, that's actually one word, not hyphenated. And non-decreasing. It's not increasing, or, sorry, it's not, it is not increasing and it is not decreasing. Okay. It's bounded. Yes. It is bounded. These values don't stray from 0. They're 0 all the time. If they're the same value for each and every term, then yeah, it's bounded. Value is always 0. So you would say that it's bounded from both above and below. And maybe we'll do one more. Just want to give you a plethora of opportunities here. Let's see. The last one we're going to do today is 2 minus 3 over n. Okay. All right, so again, think about what these actual values in your sequence would have to be. If n equals 1, then your first term would be 2 minus 3. If n equals 2, you'd be doing 2 minus 3 halves. If n equals 3, n equals 4, n equals 5, n equals 6. Note that you started off by taking more away from this value. So 2 minus 3 is negative 1. 2 minus 3 halves is 2 minus 1.5, which is just going to be a half. 2 minus 1 is 1. 2 minus 3/4, well, now you're looking at 8/4 minus 3/4, which is 5/4. 10/5 minus 3/5 is 7/5. Look at what's happening to these values. 2 minus a half is 1.5, which is 3 halves. So you're seeing that the values, let's see, 5/4 is 1.25, 7/5 is 1.4. Of course, here we have 1.5. You're trying to figure out, like, is this pattern going to hold? Because I'm seeing that these numbers started out being negative, we went positive, and now we're seeing that these values continue to increase. Like, is that going to keep happening? I feel like there's definitely enough, I hate saying I feel like, there's definitely enough evidence in this case to suggest that, because think about what you're subtracting from 2 each time. The value that you're subtracting from 2 each time is getting much closer to 0. I mean, if you were to take the limit of 2 minus 3 over n as n approaches infinity, you would get 2 minus 0, which is 2. So what that means is that these terms are eventually going to head to 2. We can now state that this must be bounded, this sequence must be bounded by 2. So we would say it's bounded above by 2. And also we can conclude in this case that it's bounded below because you don't see any value that's less than -1. So you have that. So we have that it's bounded both above and below. Sorry, I gave you 3 examples where we were always bounded above and below. Either way, is it monotonic? We would have to say that, yes, in this case, your values are increasing. Now, they're going to be increasing all the time because, oh, actually, oh, yes, what was I thinking? Yes, they are going to keep increasing. So we would say that this sequence is monotonic because it's increasing, because the terms are increasing. So this value is going to keep getting larger because you're taking a smaller amount away from 2 each time. So it's going to keep heading towards 2. Eventually, this value will head towards 0. Monotonic, increasing. All right, so I'm going to assign you some homework so you can get your feet wet on this. And we're going to work on 8.2, which is series on Wednesday. We're going to take a little bit of a departure. The series stuff is similar, but also completely different. So same type of thing, but applied to a different type of function. And then pretty much after that, we're going to keep working on series and just test for convergence. So like today, we were able to figure out like that our sequence was converging to a specific value. It's not going to be the same with most of the series that we work with. You're going to be doing a lot of tests to determine like, does it converge or not? And then you're not going to be able to actually tell me in most instances the value to which your series converges. So with sequences, it's kind of a little bit easier just because you can actually say like, yeah, it converges and to this value. It's much easier to just write out the list of a sequence versus like adding up sums for your terms. So, all right, so that's what we're going to do Wednesday. We'll be working on 8.2 and we'll probably start 8.3. Do I want to do a quiz Wednesday? Yeah, I might give you a little quiz on this. It's a good quiz material. And we don't have a test or anything, so technically I'll owe you a quiz. It'll just be over 1 section instead of 2. So that's kind of good for you, right? All right, that's it. I'm going to have your test graded by Monday. I haven't started them yet, but I'm going to start them tonight. Oh, you don't know what tonight is. Tonight is Thursday. Maybe for you, it's Monday. Okay. All right, that's all. Have a wonderful, wonderful evening, weekend, day. I don't know when you're watching this. All right. Email me if you have questions.